So before we go much further, let's see if we can figure out why is momentum conserved. Well, momentum conservation, it does arise from Newton's laws. Let's start with Newton's third law. Now, if you remember Newton's third law, every action has an equal and opposite reaction. But a better way of saying it, just for clarity, is if object A exerts a force on object B, then object B will exert an equal and opposite force back on object A. And if we have, let's go back to our ice skaters here, because it's quite useful, because we've got object A, which was this person here, for example, and object B over here. Well, if they are stationary and then push each other apart, then they apply an equal and opposite force on each other. So person A, or object A, is going to push object B away, or person B away, with a force in that direction. I'm going to call that force F. I'm going to call it F A on B, because it's the force of A pushing on person B. But what Newton's third law tells us, of course, is that there's an equal and opposite force comes into existence at that moment. So it's exactly the same size, but in the opposite direction, which is person B pushing on person A. That is what Newton's third law tells us. So I can actually say that the force of person A pushing on person B, or object A on B, is equal to minus the force of object B on A, or person A on person B. So we have a kind of statement that basically is a statement of Newton's third law. But now we're going to bring in Newton's second law. And Newton's second law, we know there's an equation F equals m times A. And I'm just going to apply that to each of these forces. Well, the force of object A on B is going to cause an acceleration of object B. So I can write down that Fa on B is really the mass of B times the acceleration of B, because that's what that force is going to cause to happen. And in a similar way, the force of B pushing on A is going to cause an acceleration of A. So I can write down that minus FB on A is minus MA AA. So hopefully that makes sense. And now I'm going to remember my definition of acceleration, because acceleration is just rate of change of velocity, as we know from mechanics. So then I'm going to substitute into the equation again, and I'm going to say, well, that means that the mass of object B times the rate of change of velocity of object B, delta VB by delta T, is equal to minus the mass of A times the rate of change of velocity of A, delta VA by delta T. So all I'm doing is using A equals delta V by delta T. Now, the delta T is the same in both cases, because the push lasts the same time for person A and for person B. So the delta T's cancel out, and I just get this interesting thing. I get that the mass of object B times the change in velocity of object B is equal to minus the mass of A times the change in velocity of object A. But if we look closely at that for a moment, we can see something pretty interesting. The mass times the change in velocity, well, that must be the change in momentum. The mass hasn't actually changed, but the velocity has. So I can actually rewrite that in a new way. I can rewrite that as delta PB, the change in momentum of B, as a small b, is equal to the minus the change in momentum of object A. And so, wow, look at that. What have we got? We've got conservation of momentum. And let's just kind of put a box around that, because that's pretty amazing. So from our Newton's third law and then using Newton's second law, we've managed to prove conservation of momentum. Pretty cool. So we're going to look a bit more closely now at the effect of a force on a body's momentum. And because hidden away in what we've just been looking at there is something called the impulse equation, which is a really important equation, which is used a lot in exams. So this time we're going to start from Newton's second law, and we're going to find an alternative expression for Newton's second law, which is what is known as the impulse equation. F equals ma then, and remember that a we can write as the rate of change of velocity, just like in the last little section. And of course we could write that as v minus u over delta t. V is the final velocity and u is the initial velocity. Well, if we substitute that in, then we get F equals m multiplied by v minus u over delta t. But what we can then realise is that if you expand the brackets, then mv minus mu is something we know. It's the final momentum minus the initial momentum, because mass times velocity is momentum. So what we've really got there is F equals delta p by delta t. So this is an alternative expression of Newton's second law. I'm going to rewrite that. I'm going to write it in a different way around. I'm going to write F delta t equals delta p. Now, why am I writing that way around? Well, the reason is because this F delta t is what's known as impulse. So this thing here, force times time, is called impulse. What does that mean? Well, it's the force acting during a collision or interaction multiplied by the time taken for the interaction. And that product is what's known as the impulse. And we can see that it's equal to the change in momentum, delta p, quite interestingly. So that's the impulse equation. Next we'll see how it works and have a go.